Okay. So your first report is due, I guess, in about a week time. Less than a week, right? Yeah. And you have a break coming up too.
Actually, it's not spring break then. I think the next.
Oh, is it the next week?
April 8th. So 7th is the last day.
Oh, okay. I had it wrong. Okay. Thank you. I will fix that.
So it's supposed to be after the spring break?
Which one?
The
The preliminary report is not, as it was as scheduled before. You have time for the final report. Right? What I'm going to do today, I'm going to give you one assignment, one last assignment I promised. So there will be 4 assignments. This is an important topic.
But
So
when we do till the.
this you can take as long as you want till the end of the course. Okay? But I will put it up in the next day or so.
That's
on the
not a
move.
good thing, but we are liking it right now.
If you are well organized
Monday.
in time, you would do fine.
No, spring break is starting
April, it starts at April 9th. Oh, 8th, I think. To 16th.
April 9th.
Yeah. 1 week.
You think you have time to catch up, but it just goes like that.
Yeah.
Okay. Are there any questions on about anything that we are doing? How do you find the course so far? Is it valuable, educational? Yeah.
I went through a couple of literature related to my project. I don't find any similarity between the models they use and what we have in COMSOL. It's like
Yours is what? 2 cylinders.
2 cylinders.
Right? Laminar flow or turbulent flow?
Turbulent flow.
COMSOL has turbulent flow models.
It has turbulent flow, but
I think you're saying it's finite element in console, but like they use finite volume or some other method.
COMSOL is finite volume.
It's finite volume.
COMSOL uses finite element. Fluent and open form, they use finite volume. Yeah. But what was your question? What is your concern?
They use SSL method.
Oh, yeah. The turbulence model is, there are many different modeling approaches to it, right? So you can start with K epsilon to explore. That's built in there. Yeah. And then the Reynolds stress model should be there in COMSOL. But COMSOL is behind in terms of the menu of modeling options for turbulent flow, also for multi-phase flow. Fluent is kind of ahead of that. COMSOL is catching up very rapidly, I think. But you can try the K epsilon model to begin with. Yeah. You will learn something. You will say that maybe K epsilon model is not doing as good a job, and you will explore why that is, and you can understand and interpret and write that in a report. That's fine. I'm not expecting the report that you produce to be publishable. Then only we need to worry about fidelity and all the other stuff. It's essentially going through the process in a miniaturized fashion of how you would do research. How do you do the literature search? How do you set up the problem? How do you get the results? And do some sort of an interpretation analysis. As I said, maybe 1 or 2 may want to, because of the passion, continue beyond this and take it to a publication. And this has happened almost every time I have taught. At least one student will say, I want to continue this. Starting from 1985. I've done this in a long time. And students, at that time you don't have COMSOL or anything like that. You need to write your own code. But students are enthusiastic.
Also, you said they are a square cylinder.
Yeah.
And then you talked about the distance between these two has to be 2 times the diameter. So I didn't understand what do you mean the diameter of square?
There is this concept of an equivalent diameter for non-circular shapes. So you can use that.
The diagonal, right?
So you know what is an equivalent diameter, right? 4 times the cross-sectional area over the hydraulic wetted perimeter. That's a definition for non-circular objects. How do you find an equivalent diameter? You can use that, or you can use the side. In fact, for a square, it turns out to be the side if you do that definition, the width of the side. Okay.
Temp is limit. It's the limit, or you expect like exactly that, like.
Which one?
So first report is 10 pages, you said, right? Limit. So is that just the limit, or you expect exactly? You care more about the materials than.
I care more about the material, so, and how well it is constructed, how logically it is constructed.
Because this part is just literature review and formulating the problem, right? So we don't start doing any.
No results, nothing like that. Yeah.
And also, you said like the next 15 pages will be continued to this, but like, for instance, I say I'll work in console and like I can formulate, but like while working through console, I find some of my assumptions not workable, so I can still change.
Oh yeah. You are free to formulate the problem as you go along. Just keep me informed. Okay. For example, when he says this turbulent model is not available, just let me know so that I can kind of keep abreast of what you're doing and guide you into what model is acceptable.
Okay, so even this can be updated.
Yeah. All I'm trying to do here is stimulate your thinking and give an opportunity for you to learn. You can learn as much as you want, as little as you want, and my grade, unless you really decide I'm not going to put in any effort, is going to be binary, A or B, right? And so I hope all of you will put some effort to get into one of those. I won't have to face that challenge. Okay, but other than that, it's essentially talking about at an advanced level what are the computational models and tools and methods, and developing an appreciation for that. So we have been talking about numerical methods, and we still have a long way to go, but I do want to survey all the concepts in terms of numerical methods that are used in advanced simulators like COMSOL and OpenFOAM and Fluent. So we talked a lot about linear systems, large linear systems. The key ideas were the direct method versus iterative method, advantages and disadvantages in each one of them, and what does that mean when you say direct method? You can get to a result in a finite number of calculations, but the round off error that it accumulates cannot get rid of it. Iterative methods have a natural way of getting rid of them, and also they are extremely efficient for very, very large systems. When I'm talking about very, very large system, literally talking about 10 million, 20 million, 40 million equations or so. And they are easily parallelizable, and we saw the ideas behind conjugate gradient method for iterative method. We also saw a number of other methods like Jacobi, Gauss-Seidel, etc. But among the powerful tools, LU decomposition for direct method and conjugate gradient for iterative method are the foundations. There have been improvements on that. In the direct method, it will be sparse, ability to handle sparse matrices. In conjugate gradient method, there are extensions to non-symmetric matrices and other, again, parallel implementation efficiencies, etc. These have been codified, so we don't really need to develop these algorithms. We just need to know what they do and know how to use them. Okay, but we don't have to write the code. ScalaPack, LabPack, they have all been developed in encoding all these concepts. And then we started reviewing about linear dynamical systems. Last lecture, we talked about the concept of Lyapunov stability, which gives us a qualitative measure of how to determine stability of systems without having to solve. So we saw two methods. One is linearize the equation, solve the problem, get the eigenvalues. That gives you whether the system is stable or not. The other one is using the Lyapunov function, which is positive definite and its gradient is negative definite. If you can find such a function, that function depends on the f in the original problem of dy dt equals f of y. And if you can find such a function, then you can say that the equilibrium system is stable. And then we saw the idea of global stability, asymptotic stability, local stability, etc. Today I want to go into building to nonlinear systems. And the example, the problem that we are going to talk about is of this form. is my pen not working? I guess. Okay, I hope I can now, yeah. So the problem is, my pen is dead. I may have to. Hmm? I thought I did. Oh, okay. So dy dt equals f of y with some parameter p in the problem. Okay, so a lot of dynamical systems can be represented in this form, and y would be a vector, and so the f would be a vector, and p could be a vector of parameters. A good example that I'm going to talk about today is actually a problem that you have already seen, a CSTR. Okay, so you have a stir tank reactor, and you have a feed that comes in, and there is a reaction that is taking place and a product that is taken out. And A is the concentration of the species and T is the temperature. So there is a cooling coil in there to control the temperature. And you can see that there is a heat transfer, which is the heat removal. This is the heat generation term, and this is the energy input minus output. That is equal to the rate of energy accumulation on the left-hand side. First equation is rate of mass accumulation equals mass input minus mass output minus the amount of material that is consumed in the reaction. So they come from mass and energy balance equation, but these are two nonlinear differential equations, dynamical systems. So the vector y in our case would consist of these two variables, A and T. A is the concentration. This was studied in the 1950s by Amundsen, one of the very famous chemical engineers, father of mathematical methods in chemical engineering. And at that time, remember, 50s, we didn't have very powerful computers, so they had to do this using just brains and analysis. So it was a publication, it was a thesis, etc. But now it's an assignment, and it's a class problem that we can use it to solve. So they found a set of parameters, reasonable parameters, to solve and analyze the solution of this problem as they changed one parameter. And the parameter that they picked is the flow rate. Q is the flow rate. So it's called a distinguished parameter in the sense the parameter affects the solution in a very unique fundamental way. There are a number of other parameters there, kinetic parameters, the heat transfer coefficient, the inlet temperature, the inlet concentration. They're all numbers. They're all parameters. The unknowns are simply A and T, and both of them are functions of time in general. So the question of interest is, how does that solution to this ODE look like? So we're going to see later on algorithms for ordinary differential equations. For now, we're going to call this as the first function. We're going to call this as the second function. And our question is, when are these functions zero? For what values of A and T will these functions be equal to zero? Okay. So keep this problem in mind as we are talking about the more generalized representation of this as dy dt equals f of y comma p, and the steady state solution implies that f of yp is equal to 0. That means find y that satisfies this equation for a given set of parameters. So we had about 10 parameters. They're all going to be constant except for flow rate in our case. And I will show you a MATLAB implementation of this. But I want to first talk about the ideas behind Newton method, the Euler-Newton method, the challenges in the Newton method. How do we implement it? All these issues. Okay. So we have already talked about Newton method for a single algebraic equation. as a linearization of the function. And when you do that for multiple system of equations, the algorithm simply is the following. Y at n plus 1th iteration is equal to y at the nth iteration minus j inverse f. These are vectors, okay? And these are evaluated at the nth step, nth iteration. So n goes from 0, 1, etc. So what we need to do is, this is an algorithm. So all we need to do is put a loop around that, but have a means for calculating j and calculating f. F calculation is very easy because they are given the two functions. But what is j in this case? J is the Jacobian matrix, if you remember, right? So in our case, in the 2 by 2 case, it will be essentially df1 dA, df1 dt, and df2 dA, df2 dt. So immediately one problem comes to the fore. What is that problem? If I'm going to use the Newton method, I need to construct the Jacobian. That means I need to go and take the derivative of these two complicated functions with respect to a and with respect to t. So if you're taking, so the first thing is for steady state problem, z is equal to 0. So this function is equal to 0 and that function is equal to 0. So when you take the derivative of this function with respect to a, that's not that difficult, right? It's going to be simply minus q, and then the derivative of a with respect to a is 1. And then here also a appears linearly, so the derivative of a with respect to a will be 1. So it is minus pv e to the power minus e over r2. Okay? That will be the first term in the Jacobian. And when you take the derivative of the first function with respect to t, what happens? This becomes 0. And you need to take the derivative of this as that term multiplied by minus e over r 1 over t squared, because you have 1 over t. So you need to apply the chain rule to take the derivative of this. So as the problem gets difficult, as we have million equations or a billion equations, this part can be very time consuming. To take the derivatives, you need to automate that process, okay, and construct the Jacobian. But you need to write a function that will calculate the Jacobian matrix. In our example, 2 by 2 matrix, yeah.
The determinant of Jacobian has to have a certain condition, like it should be 1 or less than 1? No?
No. There is only one requirement on the determinant of the Jacobian. That is, we want to invert the Jacobian in this step. That means it must be invertible. What does that mean? It cannot be a singular matrix. Its determinant cannot be 0. But it can be anything else. It cannot be 0.
I remember in one of my models, I don't remember exactly how was that, but the error that Console gave it to me was like the Jacobian method is not converging. It had something to do with Jacobian. So in numerical method, what should happen that Jacobian doesn't?
Your question will be answered at the hopefully end of this lecture, because this is what I want to build up to. Okay, so this is the requirement. I'm glad that you raised this point. This should be invertible. That means it cannot be singular. But that doesn't mean nature obeys all that time, right? You can have a problem where it will become singular. In this particular example that I'm going to take, it does become singular. Okay, so a clever mathematician then says, what is happening at that point when it becomes singular? How can I use that condition to see how the solution structure changes when I change a second parameter? So it's really a powerful set of tools, very simple tools, but powerful set of tools that we will develop hopefully today. Okay, but keep that question in mind. If I don't answer it, remind me about it. But at this point, all I need to know is I need to write a routine to calculate the function. I need to write a routine to calculate the Jacobian, and of course I can invert it in MATLAB, and COMSOL does it automatically internally. That involves solving a linear system. So to find this term, you need to solve a linear system at every iteration. So the iteration n equal to 0 means you need to give the first initial guess, right, for y, which consists of a and t. You need to give it the first initial guess. Okay, and you will see all this in the code that I'm going to show you at the end. So you provide an initial guess, take that guess, plug it into the functions, calculate this. plug it into the Jacobian, the derivatives, 2 by 2 matrix, evaluate that. Then evaluate this product from the initial case, subtract that, that's your next guess. Now, this method converges quadratically. What it means is, if the error at a single step is 10 to the minus 4, one more iteration will take it to 10 to the minus 8, one more will take it to machine precision 10 to the minus 16. So the error essentially goes as a square. Okay? So it's an extremely powerful method. The only drawback, there are two drawbacks. One is you need to evaluate the Jacobian, the derivatives, analytically. And the other one is you need to come up with a good initial guess. If the initial guess is bad, this can blow very quickly. Okay? It has nothing to do with the Jacobian being singular, it's just the initial guess is poor. So we need to come up with a mechanism to develop better and better initial guesses as we continue the problem. Okay, any questions?
Can we see from that code why the initial guess affects? Because what I say is you are subtracting the J inverse, so why a bad initial guess would go up?
I can give you a way to think about it in a one-dimensional case, and something equivalent will occur in a higher dimensional case. Okay, so suppose I have a function that is like this. The function has 3 roots, okay, and my guess, I don't know where the roots are, so I pick my guess somewhere here, x naught, and I can go to this or this, okay. But what does the method require in a one-dimensional case? It requires xn plus 1 as equal to xn minus f divided by f prime. The f prime in one-dimensional case is essentially the derivative. It's equal to the Jacobian of a multi-dimensional case, but its division, there it appears as inverse. So you can immediately see what happens to f prime there. It's almost 0. So you have a divide by 0. That is the same condition, singular matrix here, divide by 0. Determinant is 0, right? And what does it do when I divide by 0? I'm trying to, in traditional Newton method, if I picked a guess here, I would say I'm going to linearize that function around that. Oops, my function disappeared. Okay, linearize it around that and find the tangent, see where the tangent intersects the x-axis. That's my next better guess. But the tangent at this point is somewhere far away. So I'm taken from that guess to a faraway location, and it becomes even more difficult from there to come back to the steady state. That's one way of geometrically thinking about what the problem is when the Jacobian becomes singular. Okay, any other questions? Okay, so I'm going to switch back and forth. So let's switch to MATLAB function that implements this. So here I have, let me start MATLAB. So all the concepts that we talked about, I'm going to illustrate in the code, and I will upload all these codes so that they are extremely useful for you when you do another problem using all these ideas. Okay. So here, let me open the Newton method. No, that's Euler-Newton continuation. That's Newton method. Okay, just a piece of code that I wrote, and so fun and dfun are pointers to the two functions I'm going to write. This Newton method can be used with any nonlinear system, but I need to define what the two functions are and the 2 by 2 matrix is. So fun is going to take 2 guesses, or maybe 10 guesses, depends on what the size of the problem is. It's going to take a set of guesses for x and return a set of function values. And dfun is going to take the same values in x that you see here and return n by n matrix out of that. Okay, and this is MATLAB syntax, and you can very easily see what the iteration is. I'm setting up 100 iterations as a maximum. I'm making a call to that pointer. So fun is the name of the function, and this is the initial guess for that function. Okay, and that will evaluate the function and return the value. So this will be a vector of function values. Then I make a call to dfun with the same x values, and I get the derivative. I store it in a variable called ft, right? And then I am evaluating the norm of the function and the norm of the x and printing it. just to show whether it is converging or not. That's just a cosmetic one. But the algorithm itself is just one line, x equals x minus fd over f. The backslash operator is in MATLAB equivalent to the inverse function, right? So fd is a matrix, n by n matrix. This is the function. So it's an inverse of fd times f. And this is the original guess, this is the new guess. So I'm replacing the original guess with the new guess. So I'm not using two different variables, the same variable. At the end of this, I will have only the new value. Okay, and if the tolerance, if the residual is less than the tolerance, I return the value. Okay, take x, x is my root, and I quit. Otherwise, I keep going 100 times. And if it is 100 times, if I don't quit, then I come out and put a message saying I finished 100 iterations, it hasn't converged. So it's a fairly simple algorithm if you are using a high-level routine like MATLAB, because the inverse routines are all essentially a very simple syntax. But what you need to know next is, how do these two functions look? So if I look at CSTRF, that is the two functions that I showed you. I'll flash it one more time. So I'm writing, where is that? Here. I'm writing these two functions. Okay, just the function, the right hand side. So I need to define all these parameter values, okay, that you see here. All these parameter values have to be defined in that function, and a and t will be packed into a vector, and that comes in x. And lamb is, I'm planning ahead, is my parameter that changes q. Everything else is constant and the values that are given here. But q is the only one that's going to change with every call I make, because I want to construct a solution for q equal to 1, 2, 3, all the way. As I change the flow rate, how does the reactor performance change? That's the question I'm trying to answer. Okay, so these parameters are the same, and you see I take from the first variable, put it into a, second variable x, put it into t, and take lamb and put it into q, and I code these two functions exactly using the same variable names, because I have created those variable names exactly the same. The vector comes in x, but I unpack it and put it into a and t, so that I can use a here instead of x1. Okay, so the chances of making an error are smaller. So that's how simple it is to write the function. Any questions on that? The last piece is you have to write the function Jacobian. Okay, the structure is exactly the same. You need to provide a guess x. You need to provide what is the parameter that you're changing, and other constant parameters are defined internally. You can pass them globally, whatever you want. And then what do you think will come after that? The derivatives of those two functions. So there will be 2 by 2 matrix that you need to construct using all these values. So once again, I take x1, put it into a, x2, put it into t, and j11 is the derivative of the first function with respect to a. j12 is the derivative of the first function with respect to t. Okay, so that's why you see here minus 1 over t becomes 1 over t squared. Second function with respect to a, second function with respect to t. So it returns a 2 by 2 matrix to whoever called this function, right? So in the return argument, you will see only j is returned, whereas in the previous one, it was only f that was returned. Any questions on these two parts?
What happens if it is like singular?
What happens if j is singular?
In the CSTR function.
Yeah.
Is there a permission to insert that in case the backslash?
No. Right now, all we are doing is in these two functions, CSTRF says give me two values for guesses for x, and I will return the two function values. And you do whatever you want to do with it. And similarly, CSTRJ says give me those two guesses, and I will return a 2 by 2 matrix. I won't even know whether it is singular or not. It's up to you to decide what you want to do with it. So the calls to these two places are going to come from Newton, because it is a Newton method that made a call here, right? Made a call to fun and defun, and then took those values and calculated. So if you are detecting singularity, this step will fail. MATLAB in this stage will catastrophically fail, saying singular matrix and quit. Because we are not testing whether FD is singular or not. Okay. Any other questions? There are situations where it becomes singular, and there are ways of overcoming that singularity.
Like we could put it on a loop, we can compute the singularity just before that state.
That would be very inefficient. You don't want to calculate singularity, right? So the efficient way is to assume that it is non-singular and just continue. Yeah, continue the solution. And when it fails, worry about why it fails. Okay, and then come up with a scheme. Or at least that's the way I'm developing the story. Okay, but nobody would essentially. I'm wrong. There are reasons why you would monitor the determinant, because the determinant becoming 0 is an indication of something else physically that is happening, that is stability changing. Because remember, when does stability change? One of the eigenvalues crosses from the left part to the right part. That is, if it is negative, the real part is negative, you have a stable system. The real part is positive, you have an unstable system. Now, as you change q, for example, there may be a particular value of q where the eigenvalue just becomes 0. And then the stability changes. Okay? And when the eigenvalue is 0, what happens to the determinant? Is 0. Because what is the determinant? Product of all the eigenvalues. So if one eigenvalue is 0, that means the determinant is 0. So the monitoring the determinant sign going from negative to positive is one way of monitoring when the stability changes. The other way is to calculate all the eigenvalues and see whether they're all negative or not. Okay. So this kind of algorithmic framework brings together a lot of things that we have been talking about. Stability is tied in dynamical systems to these methods. Any other questions? Okay. So let me go back to this main function. This is my driver. I'm solving all the various parts I'm going to show in various sections. So in the first highlighted section, I create the initial guess vector. X equals 0.008, 320. 0.008 is the initial guess for the concentration, 320 is the initial guess for the temperature. I could have put any number because I have no clue, right? And I will normally end up with a blowing up system. It doesn't converge. This is why Newton method has to have a good initial guess. If it has a good initial guess, it converges like a charm in 2-3 iterations. If you have a poor initial guess, it'll just keep blowing up on you because it takes the gradient far away. Okay? And lamb is, as I said, my parameter that I'm varying, which is q in this case. And then in the fourth line, I'm making a call to Newton. I showed you how the Newton method looks. And it makes a call to CSTRF. This is where the mapping is done. Because within Newton, I just call it as fun and defun. So fun is now going to be mapped into CSTRF. For your problem, you may call that problem that you're solving something else. So you replace the correct name of the function. And it says that x is the initial guess and lambda is the parameter. And so this function has two input arguments, x and lambda. So I'm identifying by the syntax, x is the one that's going to be choosing the sum. Same thing here. Okay? And then this is the guess for x. All this comes from the first line. Wherever x appears, substitute there. And what is this one? This is the tolerance that I have built inside the Newton method. Okay? And the last parameter is a flag which says if it is 1, print every iteration. And if you go back and look at the Newton method, you will find that I'm using the tol function here. That's the tolerance. If the absolute value of f is less than tolerance, it's converged. So I take the x, put it into R is my converged root, and I return R. But I also return the iteration number and the residual. Okay? And as I said, the last one is the trace, which is used here. Like if it is active, if trace is true, then print every iteration. Otherwise, don't print. Okay, so just give the final result and move on to the next parameter. So how does it work? I can just run that part of it. Let me just move.
So since you have already given at x, why should you give that x after the CSTRF?
That's the syntax that MATLAB has. Your question is, since I have indicated here, why should I have it here?
No, yeah, I mean you have already defined x as unknown in this part, and you defined x as unknown in the first function, but then you didn't do it in the second part.
No, I did. This x goes with this function.
Oh.
This x goes with this.
Okay.
And you have to do that. That is the syntax of MATLAB.
Yeah, I was looking at that.
All right.
So lamb is the Q value. Right?
Lamb is the Q value,
So
right.
we are initializing it like you said that lamb would be varying from a particular value. To a
So what I want to do is I want to construct a solution that I'm going to plot. Let me just go to my scrap page. Okay. So what I'm going to do is this is my goal. Q going from point 1 to 30. I'm going to plot T and A. So I want to know how the solution changes as I increase the flow rate. Okay, does it just monotonically smoothly change, or does it have some funny behavior? It turns out that it has funny behavior, and that opened up the whole area of nonlinear stability and multiplicity of solutions in reactors. Not literally hundreds and hundreds of papers were published by Emerson and his group, and Balakote and last number of people did that. But this was one of the early problems that highlighted that feature. Okay, so let me just run this, and when I run it, this is what I get. Okay, so what has happened is it has executed the first four lines and spitted out the results coming from Newton. And what you see here is the first is the iteration number, the second one is the value of x, and the third one is the norm of f. Okay, iteration number, norm of x, norm of f. Norm of x, what should happen if it is converged? It should stay the same. If it is converged, x equals x minus j inverse f, j inverse f would be 0, f would be 0, right? So x is going to be the same. And you can begin to see that, right? For 7th, 8th iteration, it is the same up to 5 significant digits. But the f tells you even better that the error was not, the guess was not a very good guess, right? So starting from an error that was fairly large, 10 to the 2, the function, when you plugged in these two values to the function, you get a residual of 516, which is 0. So it's a terrible guess. And it brought it down and then went back, seesaws. But once it gets close to the root, you see the quadratic convergence, 10 to the minus 2. In one step, it goes to 10 to the minus 4, 5. In another step, it goes to gain square n, approximately. Why doesn't it go to 24?
The changes are very small.
That's an important question. Conceptually, we have talked about it. That's quadratic convergence, right? Quadratic convergence says it should go as square of it. So I see square here, I see approximately square here, I don't see square there. That's a kind of question I will ask you in the oral exam. It's a very simple idea. Anybody has why explanation of why it doesn't go to 24? What is the machine precision for MATLAB? 10 to the minus 16, right? So the number of bits that it has in MATLAB can represent only numbers that accurate, 16 significant digits. So it cannot take it there. At this stage, it is round off error dominated. Okay? So if you are really interested in calculating something that's more than that precision, what do you need to do? You need to manage this allocation of storage space. So it is possible to do higher precision calculations with MATLAB, with Mathematica, so what they call arbitrary precision. But these are all handled algorithmically, not with the hardware. The hardware assigns only 8 bytes per word or per variable. That can represent only about 16 significant digits. Okay? So any questions? That's the first part. So you understand what Newton method is, what you need to do. You need to write a function, you need to write a Jacobian, and you need to write the Newton method itself. Newton method is a generic tool. The functions are very specific to the problem that you are solving. Okay? And so I got a solution for one value of q, 0.1. Now I want to solve the problem of getting the solution for a whole range of q. So what I have is, I have some number here, some number there. And how did I arrive at that number? I started with some guess and pulled it towards that, converged it towards that. Started with some guess, converged it towards that, right? If I'm farther away, it takes more iterations. But what are the options now for me to generate the next solution for 1? I have for point 1, I want to generate for 1. 1 would be use the converged result. The naive one would be use the same guess. Right? So the naive one would be to say I'm going to use the same guess, which would be something like this. For all the values, I'm going to use the same guess. And depending on how the solution goes, it may become progressively worse and worse, or sometimes better and then worse. We don't know. But your suggestion of use the converged result is a better one. Okay? So I take this and give that as my initial guess. Okay? And then I solve. Maybe it goes like that. So I can construct a solution like this. Every time using previously converged one as the initial guess. Okay? That is simple continuation. Okay? But there is, can you do better than that?
Yeah, we can use the next one and see the change, like how it turns from the first to the second one, and use both.
Right. Did you all get what he's trying to aim at? If you know, like from the first one, when you change to this one, how much did this change? Right? So you can use that information to project how much it might change the next time around. And that is what is called the Euler-Newton continuation. Okay? So what you described is a numerical way of doing it, because I have two numbers, I can calculate kind of the slope, and then project the slope to find out what the next initial guess would be, which would be better than saying the convergence result is the initial guess. But you can do that analytically. Okay? How would you do that analytically? And that, again, is an extremely powerful method. It's called the Euler-Newton continuation. Okay? So the idea is the following. F of x, which is treated as a function of p, equal to 0. This is the problem I want to solve. Okay? Now here I have explicitly written that x changes when p changes. What I'm changing is only p, the parameter. Parameter is the one on the x-axis, right? When I change p, it changes x. So this function f changes. The function f can change due to two reasons. Direct dependence on p, indirect dependence on x, and then x affecting p, right? Do you understand what I'm trying to say there? So if that is the case, I can take the derivative of this function with respect to p. Okay? So what is df dp? It is going to be df dx dx dp plus df dp equal to 0. Chain rule. Okay? So that is the essence of the Euler-Newton continuation mathematically. Conceptually, graphically, we saw in the earlier slide what it is. Essentially, I would need to take the tangent vector to the solution and project the next guess from the tangent vector. This is a way of getting the tangent vector. It's nothing but application of the chain rule, recognizing that when we change p, f directly changes p affects x and x affects p also, f also. Where is the vector, tangent vector hidden in there? dx dp, right? So dx dp is the vector that you are after. You can actually calculate that in a very simple way. What is that? Dx dp is minus j inverse df dp. What is df dx? That is your j. That is your Jacobian, right? The derivative of every one of those functions with respect to every one of the unknowns. That I already know in the Newton method. I have already calculated that at the converged value. In the last iteration, when I save that j, I have that information on the tangents, right? So if I take that and multiply it by this df dp, I get the tangent vector. So the idea, once again, is graphically, I'm plotting x as a function of p, and this is my solution at x, and I want to draw a tangent vector and calculate at x plus, p. This is at p, and this is at p plus delta p. So it's a Taylor series expansion. Numerical method, fundamental building block is a Taylor series expansion. So this is, you can think of it as a first derivative expansion. You can do this for second derivative as well. So this is the tangent vector dx dp. Is computed simply as minus j inverse df dp. Now the problem is, once I have that, I have a good projection. The projection is going to be x at p plus delta p is going to be x at p plus dx dp multiplied by delta p. So I choose what this delta p is. I choose this step. How long do I want to take a step in Q? And I need to calculate this df dp. So if I have that, and if I have that, I have previously converged result, this will be my best guess for the next step. Not the constant value, not the previously converged value, but based on the tangent projection of the previously converged value. Any questions? Now the question I have for you is, how do I get df dp? Okay, so go back and look at this equation and tell me how you will get df dp from this. What is df dp in these two equations? Df dp is going to be a vector, because f is a vector. f1 and f2 are two components, right? This is f1, this is f2. What is p in our case? The parameter, right? So what is the derivative of this function with respect to q? Partial. It's simply a0 minus a.
But a also changes to b, right?
But you are taking the partial derivative of that. Go back to this and see how the thing was constructed, right? So this is the total derivative of the function with respect to p. That is the partial of f with respect to x and x with respect to p. So we are treating x as a function of x. But here this is a partial variation, because when we are varying this, we're keeping this constant, right? So it's only the partial variation of f with respect to p. The variation of p with respect to x and x with respect to f is being taken care of by this. Okay? So you need to take only the partial derivatives of the two functions with respect to that parameter p. And that's fairly easy to do. Okay? Because the second case also p appears only in the first term, none of these contribute to that. So if I can calculate that function, then Euler-Newton continuation is extremely easy to implement. Any questions? So let's go back to MATLAB and see how this is implemented. So there is a function called CSTR df/dq. So what does this function calculate? It calculates the derivative of the function with respect to q that I just talked about. So you can see immediately. It is a0 minus a for the first term, it is rho times c times t0 minus t for the second term. So this is a vector of how the function changes with respect to the parameter. Remember, these ideas can be extended to another parameter that is varying. Okay, it can be inlet temperature, it can be inlet composition. The ideas are the same. So which parameter that you continue, you decide. And once you have that, you go back to your original function in the next path. I think I have a subsection called forward path where I set up the parameter q going from point 1 in steps of point 1 to 30. Okay? And then I have a call to a function called Euler n with an initial guess and that vector q. So this is the job of Euler-Newton to construct that curve for me as q changes from point 1 in steps of point 1 to 30. Okay? In the forward sweep. Okay? And then once it comes out, I'm plotting it. In the first subfigure, I'm plotting temperature and then concentration. So let me just run this through. And what would you expect before you run? Do you have an expectation of how that curve will look like? It's not an easy question to answer. because you don't know. Chemical engineers that are in reaction engineering may think about it and say, well, if I'm increasing the flow rate, what am I doing? I'm reducing the same reactor volume, right? So I'm reducing the residence time. So if I reduce the residence time, what happens to conversion? It lowers, exactly. Are you a chemical engineer?
Yeah, my background.
Okay.
So the Euler function essentially just gives us a better guess, right?
Oh, I haven't shown you how the Euler function looks like, right? So to see the whole puzzle. So this is the Euler-Newton function. Okay, so first I count how many entries are there in Q to know how many times I have to go through the loop. That is n. So I set up a loop for that. And then I find out the delta Q. Q is a set of vectors, right? So delta Q is the difference between two values of Q. Why would I need this vector? In the Taylor series expansion, when I have multiplied by delta Q. Remember, I showed you x at Q plus 1 equals x at Q plus dx dq times delta Q. So this delta Q is the difference between the two values. And what do I do here? I just pass control to Newton with a guess. And that guess initially is the initial guess that was passed. Okay? And so this is exactly the Newton method, but whatever comes out of the Newton method is my converged result. And I take the converged result and store it here for plotting purposes, but I estimate the derivative. So this is where I transfer the call to the Euler-Newton derivative, df dq. And this is the Jacobian, right? So this is dx dq, and this is the next best guess, which is the previous guess multiplied by the tangent vector multiplied by delta q. Once I have the previous guess, I go back to the Newton method and use the Newton method on that, right? So I take a tangent projection, Newton iteration, converged. Then I go to the next tangent projection, Newton iteration, and converge, right? So this is the tangent projection, that is the Newton iteration. And this is the loop to cover the entire range of Q. So one would expect the conversion to go down and maybe temperature to go up because you're not having enough residence time to remove all the heat. And let's see what happens. This is what happens. Okay. So what you see on the top figure is A versus Q, the flow rate. This is the concentration, 10 to the minus 3. And here, temperature versus this. But I was expecting some sort of a continuous curve going all the way. But what happened here is it came up down up to this, and all of a sudden it jumped to this, and then continued on. Okay. So what do you think is happening there? It hits a critical value. One of the eigenvalues go to 0 there. Okay, it becomes unstable. Everything funny in nonlinear system that can happen happens around such point. These are called the limit points. So there is no solution beyond the limit point. And we have seen an example of a canonical one-dimensional example where you have kind of a parabolic behavior around such limit points. Okay? So there is a solution here, and that will come around like this. But Newton method, Euler-Newton method are not able to get that solution for us. Okay? So can you think of, now that you have the code built, can you think of what would happen if I start from here and then go back, decrease Q? That's what I call the reverse time.
So it should go till the other point?
Till here?
No, it should go further.
It should go further?
Yeah, till where it turns.
Where it turns, right. So if you have that picture that there is something in between, then you will see that it goes up to the point where it turns here and jumps. And that's exactly what happens. And Amundsen actually did all these calculations through a combination of clever analytical manipulations without the computers. So it's very easy to set up that reverse path. Q equals 30 minus 0.1 to 0.1. Just reverse the direction of the vector, right? And then do the same, make the call. But this time, what does this x contain? The last conversion value from there. That corresponds to Q equal to 30, right? So that as an initial guess, try to construct the solution back, and you will find that it overlaps until that region where it will diverge. So the green one is plotted for the reverse path. Okay? So it follows exactly the same thing because there's only one steady state solution in that region. So that you go in forward direction, backward direction, you give any guess, it should go to the closest steady state. Okay? But in here, it just comes up to there and then jumps. So there is a path that is connecting these two. And at this point, the eigenvalue changes sign, the matrix becomes singular, and at this point it does the same thing. And in between, there is one positive eigenvalue. And you can calculate that. Why? Because you know J. Right? You know the Jacobian at every point, you have been calculating it. So make a call to EIG, it's only a 2x2 system, you can get an answer about the stability. Right? And you will find that the stability changes here and it changes back here. Stable. So this is a stable system, this is a stable system, in between there is an unstable system. What is more interesting is if I had picked a value of Q equal to 8, what would have happened? I didn't have all this sophisticated Euler-Newton method, I just had a Newton method. I made a call to Newton method with Q equal to 8. What do you think would happen?
Depend on the guess.
It will depend on the guess, right? If your guess is closer to, at 8, for example, if you draw a line, there are two solutions. One is the high conversion, another one is the low conversion. Okay? The low conversion and high conversion. So, if you're given a guess closer to this, it will be attracted to this. If you're given a guess closer to that, it will be attracted to that. So, we talked about in the Lyapunov stability that there is a region of attraction. Right? So, you can think of that as the region of attraction, meaning any guess that is within that will be attracted to that steady state in that region. But if you go outside of that, it will be attracted to the other one. But even if you give a guess that is right on this curve, it will not converge to that. It will diverge because it is an unstable solution. I take that back. For ordinary differential equation, if you integrate that to reach a steady state, it will not converge to that steady state to an ODE integrated. We will see later on. But Newton method, the beauty of Newton method is it will converge no matter whether the real system is stable or unstable. The numerical algorithm is always stable. It is guaranteed to converge quadratically. As long as you have a good initial guess, now we have a way of generating that good initial guess. And it's easy to implement in COMSOL. In the next class, I will show you how the same, maybe I will just put the code in Modal on how to solve the same problem in COMSOL. COMSOL has this continuation feature built in. None of the other simulators have that. We need to use some sort of a pseudo converse solution, what do you call loading. Take a converse solution, give it as an initial guess, and try it again. Whereas this is a more sophisticated way of continuation. Any question on the idea? Do you get the idea? Yeah.
So if you operate the CSTR at Q is equal to 10, depending on which temperature I run it, I'm going to obtain either one of those conditions.
Yeah.
Okay.
So that's a good question. In reality, what happens, right? In reality, depending on how you start up your reactor, you may be stuck on one or the other. And if you're stuck on the one and you want to push it to the other, what do? You give it a large kick to the system, meaning control your heat exchanger to change the temperature to take it to the other one, right? Same ideas are applicable in the Taylor-Couette flow, in hydrodynamic stability problems. When you have multiple states, how do you get from one state to the other state? Through only external perturbations that are large enough to take it away from the one stable steady state to another stable steady state.
I think we worked on something like that in one of our previous classes, like about the temperature to see how
Right,
it's
yeah. So here the focus is on the algorithm. I think we use the same problem to talk about these concepts, but here I'm showing you how these algorithms are used. What does Euler-Newton mean? What does Newton mean? And what does arc-length continuation mean? That's the next evolution in the concept. So the next challenge is, how do I get the intermediate solution? The current techniques that we have developed will not give me the intermediate solution. And that is what is called arc-length scheme. That's the next piece. And in this piece, what are the concepts? Okay. So what happened currently is the following. Okay, so I have a solution like this and then a solution like that. So if I take the tangent vector and project it, I normally got a very good prediction. But here the curve turns around. So if I take a tangent vector, what happens? Tangent vector actually projects vertically up, right? And can I multiply it by a delta q there? It is a particular value of q, right? So it is undefined, right? The tangent becomes infinite and it gets multiplied by 0, so the product is still meaningful. But I cannot get an initial guess on this side of the turning point. So this is called the turning point. Turning point or the limit point. What happens here? One of the eigenvalue approaches 0. The matrix J becomes singular. All the nasty things happen. Okay? And so the Newton method would have difficulty converging right on that value. But if you take a slightly smaller value, of course it converged here without any problem. So it will converge there also. But how do I give a good initial guess on the point? I cannot generate an initial guess from these tangent vectors. So do you have an idea? The idea that Keller, I think, came up with, Russian mathematicians have thought about this even earlier than that. There's a method called Davydenko method. But Keller's arc length is probably more problem. Keller was a mathematician at Caltech. The idea is the following. What is so unique about that parameter q in those two equations? Okay. For engineers, it is unique because it is flow rate, I can control it. For a mathematician, it is one symbol like any other symbol, right? So I don't find q to be distinguished in any way. So what he says is, I'm going to treat that as an unknown. Okay? I'm going to define a new variable, which is a measure of the length along the arc that I'm measuring, S. Okay? So I construct a kind of a curve and I measure the distance along the curve, S. And S would be a continuous function. It will go around without any problem. So instead of specifying a Q, I'm solving for A and T, I will treat Q as an unknown. But I will specify S as a known. So I specify, find me a solution at S from the origin. Okay? And that means find me a solution means find A and T and Q, because I made Q as an unknown now. Okay? So by making Q as an unknown, I have an extra degree of freedom. And that freedom can be used to define what this arc length is. So his definition of arc length, there are a couple of variations. So this is my third equation in this case. He calls it n. Okay, so another equation. That equation is actually a function of x and q and s. X is my state vector of all the unknowns. Q is the parameter, which I made it as an unknown. And S is a known parameter, which is a measure of the arc length, measured from some point. So one way of writing this would be summation of xi minus xi naught square over all I, plus maybe you can put a weighting factor there, W1, W2, qi minus qi naught square equals S minus S naught square. What does this equation remind you of? If I write an equation like that. It's an equation for a sphere. It's a generalization of Pythagoras theorem, whatever way that you want to look at it. So it's essentially, this is the radius of the sphere or a circle. Okay? And these are the coordinates, and x0, q0 are the origin around which that sphere is constructed, right? So if I take a point like this as my reference point corresponding to x I is 0 and q is 0, what I'm doing is I'm drawing a circle. So one solution is this curve, which is determined by f equals 0. What is the property of this curve? F is 0 on this curve. I found out the solution such that f is equal to 0. Here is another curve which is given by n equal to 0. right? So you can write this as left hand side minus right hand side is equal to 0. Okay? So this corresponds to n equal to 0. This corresponds to f equal to 0. What are the 2 points where both are 0? At the intersection, right? So I can specify, I can make my delta S bigger. That means I have a bigger circle, and I can find those solutions, right? I can make delta S smaller. I can change that variable. That becomes my control variable. Q is no longer the control variable, but S, the radius of that hypersphere, is the solution. What is the beauty of this? If I take a point near this and I draw a circle, I will always have 2 solutions. Okay? So I've removed the singularity. But what I have, the challenge is I have an enlarged system of equations. Okay? So I have this equation f of x q equal to 0. This is I going from 1 to n. And then I have a scalar equation, which is x q s equal to 0. So I have n plus 1 by n plus 1 equations instead of n equations by n equations. So this is called the arc length equation. This is the original problem. But q is being made as an unknown. X and q are unknown, but s is unknown. What do I have now? I have an extended system of nonlinear algebraic equations. I can apply the Newton method on this. And I can specify S, and I can construct the entire curve.
And the radius, is that something we specify?
You specify. Instead of specifying Q, you specify S.
Because like if the radius is large enough, we can have more than 2 solutions.
That's possible. So you need to control that radius extremely finely as you turn around. You will find that out. So you can actually implement on top of this, you can use Newton method to solve this, where you specify S. Now you have the same problem. How do I come up with a good initial guess for X and Q? You can say, oh, I can use Euler-Newton method on this extended system, right? And then you can ask the question, okay, how do I pick delta S? The previous case, I picked delta Q uniformly. Can I do something like automatically adjust my delta S? So in regions where things are going smoothly, I take larger delta S. But when I'm turning around, things are changing very rapidly. I'm taking smaller delta S. So automatic step size is one idea that we can talk about.
So we solve it once to see the jump and then refine it near the zone.
No, a clever method would be it will monitor the magnitude of df. We need to use a different set of symbols to talk in the same language. So if I combine these 2 functions and call my big function in this form, where f, big F is the vector f and n, okay, and the big X that I saw here is x and q. Okay, now I have the same Newton method, extended system, 3 equations, 3 unknowns, right? So I can apply the Euler-Newton continuation on this. And what is the Euler-Newton continuation on that going to give me? This capital dx, ds. And if that number is very large, remember around that it's going to go to infinity. If it is very large, then I take my smaller delta s. So I can monitor the magnitude of this to adjust the step length. So the ideas are not very many and very difficult to grasp conceptually, but this kind of recursive use of it make it complicated for you to grasp. Okay? So we applied Newton method on this, we extended Euler-Newton to this, we encountered some problems in turning around, we extend the system. Now we apply the Newton method on this extended system, we apply the Euler-Newton continuation on that. Okay? And let me just show you how the solution looks, and then I will show you how the code looks, and I will upload the code so that you can study them in greater detail. So arc length. So this is the one. So I want to run the last section. This is what I get. And I learned this as not as a graduate student. I did this when I was a first level. When it turned around, I was really excited. Right? So what you see here is the distance between 2 solutions. Delta S. So here it's taking small steps. It's increasing the steps. As it turns around, it takes small steps. And Here it is again taking magic steps. But it turned around in one go, okay, and found the complete branch. Now the beauty of an algorithm like this is, if your solution structure looks much more complicated, and there are examples that have solution that do this, all right, it'll just walk through it without any problem. No matter how complicated the solution structure is, each one is called a different type of singular point. This one is called a fold, that will be a fold, that will be a fold. This is a transcritical verification point. It just goes around, comes back, and then goes on like that. Right? So there are many, many types of such singular points, and in the 80s and 90s, applied mathematicians had a field day documenting and characterizing these singular points. There was something called catastrophe theory, stuff like that were developed to understand this singular nature of nonlinear systems. And a lot of numerical algorithms were developed to track each one of them. For example, one of the questions that you can ask is, now I have an idea of where this limit point is, approximately, from the graph. Right? If I look at this graph, I can read from the graph maybe it is 7.5 or something. But I want to know precisely where it is. How would I find that out? What idea would I exploit to find out what value of Q exactly depended on precision, where the singular point occurs? What do we know about that singular point? It's a simple limit point. It just turns around, the stability changes, the eigenvalue goes to 0. So the question is, why can't I impose that condition? And once again, make Q the variable. So I will search for Q, but calculate the determinant. This is one place where you will look for the determinant. So add the fact that the determinant is 0 only at that point, nowhere else. So in addition to the original function f, you impose an additional function, set of functions, that says the determinant is 0. And then make Q the variable. Just like we added an additional equation n and made the Q an unknown but specified s. But now I'm going to solve for the single value of Q that makes that particular point 0. So if I find such singular points, the next question one can ask is, how does that singular point change when I change the temperature, the cooling water temperature? How does it change when I change the inlet concentration or inlet temperature? So very quickly you can map in the parameter space where I will have multiple solutions, where I will have unique solutions. And that's a powerful map for an operator, because he knows which to avoid and where to operate, which are the high conversion regimes, etc. So any questions? So I've kind of shown you what an arc length method is, what it can do, and the results, but I haven't shown you the code itself. The code is a bit complicated. So I just have this function called CSTR arc, and it is going to have its own Newton method, so its own Jacobian for a 3x3 system, its own function for a 3x3 system. And so let me just show you.
Second last one.
Which one? Have I opened it? CSTR FR. That's the function. Okay, maybe let's look at that first. Okay, the function looks exactly the same structure, but x is a vector and ARCP is a set of parameters that I'm using to define my arc length equation. If you look at the original notes, when I wrote this one, I said I'm going to have W1 as a weighting parameter, W2 as a weighting parameter. This is an equation that I write. I can write it any way I want. Right? Why would I want to have W1 and W2? For example, if Q happens to be on the range of 1 to 10, and T happens to be in the range of 300 to 400, I don't want my arc length equation to be dominated numerically by this term. So I can multiply this by 1/10 of it to bring it down. So the scaling factors essentially bring all the terms to be roughly of the same order. So there are a number of parameters like that are passed in that vector arc P. Okay? Arc P is a set of arc length related parameters. The problem related parameters are listed here from lines 2 to 12. So here, So from the arc length parameters, I'm taking the first parameter as W1, the second parameter as W2, third parameter as dx, ds, etc. And the delta S is my step length in the S. And then these are all looking exactly the same. X1 goes to A, X2 goes to B, Q3, the third X3 goes to Q. That's the unknown now, right? And I have three functions. First two functions are exactly the same. The third function is the arc length equation that I have to establish. Okay, and again, there is no unique way of writing it. You can write it in a number of different ways because it is entirely up to you. You are defining it. What is the measure of an arc length? What I need now is the Jacobian of these three functions. So it's a 3x3 matrix. So I need to write a function called CSDR arc, and it has the same input, and it has, if you see, the same 2x2 matrix, submatrix, but then I will have a column of vector on the third column and then the third row. Okay? So these are derivatives taken from the definition of the arc length equation. Okay? So they are fairly easy to develop. Once you have the arc length equation, take its derivative. And function arc, and where is the CSTR arc? So this is what I specify as my input to the function that is implements the entire arc length. Number of steps. Starting from this condition, take 300 steps. No matter wherever the curve goes, just go along that curve and construct the curve for a certain number of steps. Those parameters are there, and you're going to make a call to Newton. Okay, after this initialization is done, you're going to make a call to Newton. But what will be the size of X now? 3x3 system, right? And CSTRF and CSTRJ. No, sorry, this is just a 2x2 system for the initial first step. The arc length continues after the first one. So the first one is done for fixed value of Q, okay, and then Q becomes an unknown, and you define all your arc length parameters, and I am implementing Euler-Newton on the arc length. And here is the Jacobian on the arc length equation. The function, the 3x1 function, the 3x2 matrix, this is the Newton method on the arc length equation. And the terminal condition is the same. Calculate the norm, the norm is less than some tolerance, and stop, it's converged. And you can take the next delta S. Now, I'm also calculating the eigenvalues here. Why would I want to calculate the eigenvalues? To know the stability of it, right? So once I have the Jacobian of the 2x2 system, that's all I need to use for stability, not the 3x3. 3x3 is only for arc length continuation. So I take the CSTR matrix, pass it to eigenvalue, extract the real part, and flip the sign, and take the product of all that, and keep that in the sign. So I'm looking for the sign change in the eigenvalue. Okay? So the rest I'm going to leave it to you to kind of figure out, and this code will help you a lot in solving the BRA2 problem, I think, which you have solved before. And this time you're going to discretize it, you're going to use finite difference methods and apply all these ideas on the BRA2 method, BRA2 problem. Okay? So any questions on that? It's a lot of material I've covered in one lecture, a lot of simple ideas, but the implementation details would take quite a bit of time, okay, to understand. Yeah?
My question, I want to raise my question again, that the Jacobian, what requirements should Jacobian have?
Right, so the Jacobian of the original 2x2 problem, the physical problem, will become singular at those turning points.
Yes.
Okay, so the Newton method will encounter convergence difficulties. But in this case, what happened was that was close enough to the other solution on the top. So as it was coming up around here, this is the place where you will have singular Jacobian. Okay, But you have an initial guess, and I've given enough iterations, 100 iterations, that it converts to this. Okay? But so it was not exact. It becomes exactly singular only at a particular value of q. And I don't hit that value because I don't know what that value is. So to find that value is what I need to do is impose the Jacobian eigenvalue to be 0. And I will show that algorithm in the next class. That is what is called the limit point, finding the limit point. What is the value of q to the machine precision that you want, where the eigenvalue is 0 to the machine precision that you want. Anywhere in the neighborhood, it's not going to be exactly 0. Maybe very small, 10 to the minus 3, 10 to the minus 5, something like that. But that's still invertible, so it will work. Okay? So it becomes 0 exactly at such singular point. There are two singular points here. At those points, the Jacobian becomes non-invertible because its eigenvalue is 0. I'm sorry, I forgot about that because I was explaining the other things. Thank you. But does that answer your question? So that's the only place where you will encounter problems with the Newton method. Okay, so we will continue with this problem for one more lecture. I will try to illustrate it with COMSOL and then talk about the limit point determination, and then we move on to ordinary differential equations. So we've seen linear algebraic, nonlinear algebraic, then ODE, initial value problem, ODE, boundary value problem. That's where we'll branch into finite difference, finite element, finite volume for boundary value problems, and then move on to PDEs.
Do you have any explanation for the homework for the assignment? Or we need to figure it out? The previous time for the first 3 assignments, you explained something.
That's what this lecture is supposed to be.
Okay.
And the problem is going to be different, but you're going to implement all these. You will have access to the code. Okay, all these codes that I've shown you today will be on Moodle. Now, we need to make up one lecture. So I don't know how to handle this. Should I send you a doodle poll to find out when you are available? Is there, or would you, this is pushing maybe, would you mind Saturday?
Saturday?
Not this Saturday, some Saturday to make it up.
Some Saturday.
Some Saturday, as long as it's in the future.
Not this Saturday, but
All right, okay. I'll bring it up next time we meet. Yeah, I will try to do the doodle poll. Yeah.